Let's take a look at some examples now. This is an example pretty much pulled from a diploma exam, and it is exhausting to look at. It is like, literally, it just brings you down. Let's read this carefully together. During a physics experiment, we have a collision between two carts. Dynamics cart, we might have played with these in Physics 20 a little bit. We've got a collision between little cars on wheels. Okay? A group of students determines the kinetic energy and the momentum of each cart before and after the collision. We have all done lab work where we have, say, a spark timer from Physics 20 or a ticker timer from Science 10. There are ways that we can determine the speeds of these objects before and after. And if I want to find kinetic energy, I can calculate it using 1/2 mv squared. I know how to do that. So I measure the speed, I know the mass, find the kinetic energy. There are ways to determine the momentum. The momentum is mass times velocity. You'll notice, I hope, everybody, that all of the kinetic energies in all of these trials, group A, B, C, D, they're all positive. That's because kinetic energy is a scalar and it will always be positive. You'll notice, however, that some of the momenta are negative because momentum is a vector. There's a lot in this question to unpack. Here's the data. So group A, cart 1 before the collision. I'm just going to highlight group A. Group A, these are the two momenta before the collision. And after the two carts collide, these are the two momenta. I want to ask you a question right now, looking only at that highlighted stuff. I want you to determine if the collision in group A occurred in an isolated system or in a non-isolated system. So Erickson, I saw you say isolated. You're right. Why is the collision that group A observed occurring in an isolated system? Right, the total momentum before and after is the same. When I add 1.2 plus 0, I get 1.2 units of momentum before the collision, and when I add -1 and 2.2, I still get 1.2. So group A is isolated. We're going to have to do this for all of them. I want you now to take a look at group B and determine if group B is isolated. So isolated means the momentum is conserved. What you're looking at now is this row of data for group B. So you add together the two momenta before, you add together the two momenta after, and you compare the totals. I'm getting positive 0.6 before, and I'm getting, I'm getting negative 0.6 before, yes? And negative 0.6 after. That means this is isolated. We're going to continue. Before we have positive 1.6. Afterwards, we do not have positive 1.6. So this is a non-isolated system. And finally, before, let's see, 3.2 plus negative 0.8 is positive 2.4. Thank you, Alex. And afterwards, we have positive 2.4. This collision is occurring in an isolated system. Okay. I'm going to cut to the chase of the question in a second, but basically in this question, we have to find out whether each of the collisions that occurred for each of the four groups was in an isolated or non-isolated, and we also want to determine whether each collision was elastic or inelastic, which is something different. So what we are looking at now, say for group A, is we are looking at the energy in the system before and after. And the question is the collision that group A observed elastic or inelastic? Alex, what say you?
Inelastic.
Why is the collision that group A observed inelastic?
There's more energy in the before collision than the after
So we've lost energy due to
Most likely heat.
most likely heat, thermal energy. So this is inelastic. I'm just going to put these here because it's getting a little cluttered. That's inelastic. If I go on to group B, let's see, before, well, it might be close. It is. It is. That's elastic. Those both add up, I think, to 6.3 joules of kinetic energy. So this is elastic. Inelastic. And this adds up to 6.4 joules before, and I've only got a little under 3 after. And then I have 7.5 joules and not even close after inelastic. So now, and I'm just the messenger here. I'm telling you, this is what you might see on a diploma exam. We go through all of that because I, as a teacher, want to know if you can tell me, did group A observe an elastic or inelastic collision, and in which system did the collision occur? And I want to be able to ask you this about all 4 groups in a numerical response question. And I do that by using a Venn diagram. So you're going to help me out here by looking at what you wrote in the chart. And Alex, I'm going to stick with you. Group A, did they observe something in an isolated system?
Yes.
They did. So group A, I'm just going to summarize this here, was isolated. And was it elastic or inelastic?
Inelastic.
It was inelastic. So this Venn diagram has 4 regions. If you talk about region 2, you're talking about something that was both elastic and isolated. If you talk about region 1, you're saying it's elastic, but it's not isolated. If you say region 3, you're saying isolated, but not elastic. Region 4 is neither elastic nor isolated. So group A is isolated, but not elastic. It would be number 3. Group A would fit in here. Group B, keep going, Alex. Isolated or non-isolated?
It's isolated.
Group B is isolated as well?
I believe so.
Yeah. Anybody else, just to confirm? Okay, again, 40 eyes are better than 2. And is the collision that occurs elastic or inelastic?
Elastic.
It is elastic? Okay, so then you locate the position on here. Isolated is in this region, in this circle, and it's also elastic. That would be number 2. It's the overlap. It's both of those qualities. So B would fit here. And if you want to see where this is going, group A, which number represents where they are on the Venn diagram? We said group A was 3. Group B is both of them, which on the Venn diagram is 2. I'm going to look back for C. C was non-isolated and inelastic. I believe that's going to be group 4 or area 4. Right? Not isolated and not elastic. 4. And if we take a look at D, D was isolated and inelastic. Isolated would be here, inelastic would be here as well. So this is also 3. Which brings up an important point. Some people do these problems and think you're going to have 4 different numbers because there's 4 different things. You can have 4 of the same numbers. Again, this is just a very lengthy question because of all of the detail you have to sift through to get to the answer. Now let's get to the important stuff, which is collisions. Now I want to be very careful here. Question 2 says you fire a 5-gram bullet from a 3.6 kilogram rifle and the bullet moves out of the barrel of the rifle at 655 meters per second. Anybody with a whiff of common sense knows you are not going to take a rifle, take the butt of the rifle, and hold it this far away from your face and pull the trigger. We know what's going to happen. The rifle is going to kick back. right? Look at this guy's shoulder. There's lots of very funny videos of idiots online firing guns. There's a guy who held the rifle 3-4 inches from his eye. I like this next one just because I think it's really funny. And it's like, where did it go? There's going to be this kickback, and the reason there is going to be a kickback, everybody, is because the two objects push off of each other. The reason the bullet goes in one direction is because the rifle pushes it in that direction, and the reason the rifle goes backwards is the bullet pushes it back. There's a little chemical explosion that produces the two forces. This is considered a collision. It's not a collision where they're moving towards each other and hit, but it is a collision because the objects push off of each other. If it doesn't say, we consider it an isolated system. So what we're going to do to solve this problem is we're going to say momentum before equals momentum afterwards. It's a very simple question. Before is before you pull the trigger, which means the bullet is in the rifle and you're standing there. You're not running with the gun. There's no momentum before. So we have 0 units of momentum before. Afterwards, we have mv of the bullet, plus we have mv of the rifle. Well, nothing is always simple, but it is this simple. There's your equation. This is like we talk about in Physics 20, where you have to go away from the idea that which formula do I use on the formula sheet? This is not on your formula sheet. You're applying a conservation law here. So let's put the numbers in. 0 equals 5 grams is 0.005 kilograms. Again, if you haven't had me as a teacher, I think when we're in learning mode, the units can just be confusing. Don't worry about the units as long as you have the right units, kilograms. That's correct, isn't it? 5 divided by 1,000. Okay. The velocity of the bullet, or the speed of the bullet, is 655 meters per second, plus the rifle is 3.6 kilograms times the velocity of the rifle. This is a very basic linear equation. 0 equals a number plus 3.6x. You need to take this, calculate this, swing it over to the other side with subtraction, and then divide both sides by 3.6. I'll give everybody just a few seconds to calculate the recoil velocity of the rifle. So when I multiply those together, I get 0.325. Of course, I'm trying to solve for VF, so I have to subtract that.
It's 655.
Thank you. I could tell by the looks on some of your faces that I had missed something there. There we go. I get 3.275. I need to, of course, subtract that to get 3.6 V by itself. So I've got 3.275. Subtract it gives you 3.6 V. I'm going to say V is 0.91. Close enough? Okay. And it's negative 0.91. Well, what's the significance of the negative? The significance is that since we said the bullet was moving in a positive direction, the rifle moves in a negative direction. Okay. And those details are important. You can't just brush that away and go, oh, I don't want to talk about the negative. It's important. Any questions with the first example? All right, this next example has a lot of calculations in it, but we're not going to all do all the calculations. I'm going to get some of you to do one calculation, some of you to do another. Well, we got our Julie and Bill at the Calgary Stampede or the Edmonton X, doesn't matter, and they're riding bumper cars. Julie is driving a bumper car, and the total mass of her and the bumper car is 250 kilograms. She's moving at 3 meters per second, and Bill hits her head on. You do need to understand the English language means, in terms of the English language, head on means they're moving towards each other. Okay? Bill's bumper car has a mass of 325 kilograms with him in it. It's not that he's more massive necessarily than Julie. He's carrying all of the prizes he's won throughout the day. Been a very skillful game player. It's loaded up with all this stuff. And he's moving at 2.5 meters per second. Immediately after the collision, they bounce off of each other. Bill's car is going backwards at 1 meter per second. What is the speed and direction of Julie's car immediately after the collision? There's no way to do this other than to say momentum is conserved. So we start off with this principle of physics that the total momentum before and the total momentum after are equal. And then we build the formula. Is Julie's bumper car moving before they collide? Sure. That means we're going to have an MV before that is Julie. Is Bill's car, does it have momentum before? Yes, MV, and this is before, and this is Bill. I hope you see where this is going. We're going to have two more terms on the other side, aren't we? Because they're both moving afterwards. So this will be MV of Julie after plus MV afterwards of Bill. And now we have to put in all of the information. Again, everybody, we're starting off with a physics principle here. The physics principle is momentum is conserved. Once you have that, you can build a formula. This is not going to be found on your formula sheet. There's a lot of information here to keep organized. Julie has a mass of 250 kilograms. And I hope you're starting to see why I think writing in units would be confusing. We got enough going on. Julie's velocity is 3 meters per second. Before, plus Bill's mass is 325. I'm going to write down something that will be a mistake. Bill's velocity is 2.5. Who can tell me why Bill's velocity is not 2.5 based on what I wrote for Julie? Aoki? Right. If I said Julie had an initial velocity of 3 meters per second, then I've really said, you know what, Julie's velocity is positive. I've just decided that she's moving to the right. But if they hit head on, that means initially Bill is moving backwards relative to Julie. I shouldn't have said backwards. Bill is moving in the opposite direction to Julie. So I need to put here not 2.5, but negative 2.5. And you wouldn't think that's going to matter, but it will. Okay, afterwards, we have Julie's mass, which is 250, times her velocity, which we do not know, right? We don't know that. That's what we're trying to find. Plus Bill's mass, which is 325. Now, what do I put for Bill's velocity after? It's positive 1. And this is a little deceptive because you might look at the question and go, yeah, but it says Bill's moving backwards. Well, yeah, he is moving backwards, but he was moving in a negative direction first, so backwards is in a positive direction. And listen, I'll solve this with you, but this is a very simple equation to solve. It's linear, hence linear collision, by the way. There's a connection between the physics and the math here. What we have, everybody, is a number plus a number equals a number times v. I'll make it into a math question. A number times x plus a number. That is one of the most simple equations that you could be asked to solve in high school, at this level anyway. So I'm going to do a little bit of work here. I'm going to show the work. You decide how much you're going to show. This is going to be 750. I'll come back to that. This is 250V. This is 325. This will be minus 812.5. bad for a Tuesday afternoon, minus 812.5. So, I mean, the rest of it, we could figure out the left-hand side is negative 62.5. Please, somebody double check my calculation there. I'm seeing some nods. Equals 250 V plus 325. I'm showing everybody more work than you need to show. What's the physics? This, and your answer. Okay, that's the physics. I subtract 325 from both sides. Negative 325, negative 3. How is it there? Thank you. Equals 250 V. Divide both sides by 250 and get negative 1 point, I want to say 1.3. 1.55. Okay. Do the decimals terminate there, Alex, just to make sure? Okay, so negative 1.55 meters per second. And that's how we find Joule's speed after the collision. You know, when you start working on some of these problems on your own, what's going to happen is some of you are going to get incorrect answers, and you'll put up your hand and say, where did I go wrong? It's probably because you didn't put a negative where there should be a negative. All right, now comes the part, well, I guess we'll do this first. If the collision occurred over a time of 0.15 seconds, what is the magnitude and direction of the force on each bumper car? Well, what we're going to do is use F delta T equals M delta V for Joule and for Bill. Okay? And here is where I'm going to have to rely on some of you to tell me some numbers to make sure I have them right. So let's do this for Joule. F delta T is 0.15. Joule's mass is 250. Correct. Don't forget that this is VF minus VI. And Joule's velocity afterwards is negative 1.55. And Joule's velocity before is 3. Take a minute, please. Take 250 times negative 1.55 minus 3. Whatever you get, divide by 0.15. And I'm going to want to know what you get. Alex.
Negative 7,583.
Point.
0.3 repeating, sorry.
Anybody else? Okay. Think about this for a second. That is the net force acting on Joule. That is the net force that Bill's car applies to Joule, because we put in Joule's information. Joule was moving in a positive direction, and then she was moving backwards, negative force. I'll ask you a question here. What should we get for the force on Bill? Exact same number that's positive, because that's where we started. Momentum wouldn't be conserved unless the forces were equal but opposite. You can confirm that. 325, I'm going to need your help here again. Negative, so 1 minus negative 2.5. Just confirm on your calculator that when you run this through, you're going to get that 7583.3 repeating. Yes? And this is the point. You get the same force. Well, magnitude is the same, but the direction's opposite. Because this momentum being conserved wouldn't even work unless the forces were equal but opposite. That's the point. So you get positive 7583.3 repeating. And I don't care about the significant figures here because that's not what I'm trying to teach you right now. I'm trying to teach you that the forces will be exactly equal but opposite. Good? Okay. Now, and Armand, I haven't forgotten about your question, but I'll probably address it at the end of the class, maybe just with you or with everybody. But after we go through this next question, Armand, I think you'd be able to answer your question. Okay? Determine if the collision between Julie and Bill was elastic or not. So this is where we have to determine all of the kinetic energies before and after. Which means, everybody, we have to calculate Julie's kinetic energy before, don't do anything yet, and Bill's kinetic energy before, and add them together to get a total kinetic energy. And we have to do it for after. Now, EK is a half mv squared. We have to calculate 4 kinetic energies. So for people who are physically in the room, I would like everybody here to calculate Julie's kinetic energy before. It's 1/2 mv squared. You need to take 1/2 times her mass times her speed before squared. Everybody here, I would like you to find Julie's kinetic energy after. Everybody here, I would like you to find Bill's kinetic energy before. And in the last row, you're going to find Bill's kinetic energy after. And if you're joining us remotely, either from Buck or Anna, in your case at home, you pick one and do the calculation. I've got the masses up here. You might have to hunt around for the speeds, and I want you to use the unrounded answer of 1.55. And I would say to you that calculating a 1/2 mv squared is trivial in this course. It really is. I mean, I know it's physics 20. It's not like grade 6 math or anything, but it's pretty easy calculation. Eli, I believe I asked you to calculate Julie's kinetic energy before. Do you have an answer? 375. Sorry? 375. Let's see. Did you forget to square the speed? Yes. Okay, very important. Such a simple thing to forget. Did anybody else over on that side of the room get 1125? Okay, good. I asked you to calculate Julie's kinetic energy afterwards. I didn't quite catch that. 300.125, jackpot. Taylor, Bill's kinetic energy before? 1015.625, good. Teague, can you tell us what you got for Bill's kinetic energy after? 162.5, perfect. And the purpose here is to determine if kinetic energy was conserved. Now listen very carefully, because I realized a couple of years ago some people missed the boat here. They look at, for example, Julie, and they say, well, Julie lost kinetic energy, okay? And they look only at Julie, and they say, since Julie lost kinetic energy, it's not elastic. The problem with that logic is maybe Bill gained the same amount of kinetic energy. We want to look at a total. So if I add up 1125 and 1015.625 before, this is the total kinetic energy in the system before. And Armand, this is what you would do with the rifle and the bullet. But it's complicated because before there's no kinetic energy. So you'd have to look at chemical energy somehow equaling kinetic.
Yeah, I thought because of the chemical energy, maybe because of the heat, it will be inelastic.
It's probably inelastic, but for us mathematically to go back to that problem and answer that question, I don't think we can. If I add these together, I hope it's clear just looking at this, this is going to come nowhere near 2140. So what is the answer to the question? The answer to the question is it is not an elastic collision. It is inelastic. And I don't know if I have this up here. I seem to think I do. Yep. There are roughly 1,678 joules of energy that was kinetic that appears to be missing now, and it's heat and sound. Just finally, Gabrielle, how am I getting 1678? Where'd that number come from?
It's like the missing subtracted from the total.
Yeah, it's the difference. The total kinetic before minus the total kinetic after gives me the, quote, missing energy. It's not really missing, it's just missing kinetic. We have just a couple more examples to go, and the number of examples we do here is not the total number that you could possibly see. I'm just giving you a total of 3 or 4. We have a 1,250 kilogram sports car rolling to a stop. Buddy behind the wheel is looking down at his phone. I can't believe how many people drive around with their phones in their laps. It's horrible. Buddy's looking at his phone, doesn't see there's a truck in front of him. Actually, the guy in the truck is looking at his phone, I guess, isn't it? Oh, it's stereotypical truck drivers. I drive a truck. The guy in the truck is looking down at his phone. He doesn't see that the sports car has slowed to a paltry 2 meters per second. They collide, and as is likely the case during a slow vehicle collision, vehicles lock together. The bumpers tend to deform and clip onto each other, or they just stick together. How fast are the vehicles moving immediately after the collision? Well, it's a collision. We're going to assume that it's isolated, and I should maybe address this. One of these days when I remember to do it, I should really go to the note package, and for each one of these questions, I should say, during the collision, there are no significant forces of friction, which tells you it's isolated, which tells you momentum is conserved. So this will be MV before of the car. Before. This will be MV before of the truck. And this will be afterwards MV of the truck. You get my intention here. I don't think it's a very witty joke, by the way, so regardless of what I'm saying, you get my intention here that afterwards, since they're stuck together, it is one thing. It is the car and truck together. This is the physics. The physics is done. Now all you have to do is put in some numbers and solve an equation. We go 1250 times the 2 meters per second plus 2200 times the 10 meters per second equals how's my addition there? 3450? You see where Craig, where am I getting the 3450 from?
Added the truck and car together.
Right, I'm adding the two masses of the vehicles together. This is like taking candy from a dim-witted child. You calculate the stuff on the left-hand side, and then you divide by 3450. I got tired of just saying a sick baby. Just, like a really slow-witted 3-year-old. Snap your fingers and distract them, and then you swipe the candy. What do we got here? That's 2,500. Holy smokes, and that's 22,000. Does this add up to 27,500 on the left? Many of you might not even have done it that way. No, it doesn't. 24,500, yeah. Equals 3450. I'm going to take a stab and say 7.
Pretty close.
Pretty close?
7.1.
7.1. I was going to say 7.1. I was. And if you believe that, I'll tell you another. I do want to point something out to you. This totally makes sense. The car went from 2 meters per second to 7 meters per second. It gained roughly 5 meters per second. The truck went from 10, and the truck slowed down during the collision, to 7. Why did the truck slow down? Not as much as the car sped up, because the truck's mass is so much greater. One final question before we do. Take a look at our work here. Does anybody have any questions you would like about, any questions about anything we did there in that example? All right, one last quick one. What do we got going on here? 1,100 kilogram car is moving at 20 kilometers per hour to the right, collides with a stationary vehicle of unknown mass. They lock together and move off at 8 kilometers per hour. Okay, so before the collision, you have the car, and that's it. The truck is stationary. You'll notice I didn't bother to write PI equals PF. We know that. After the collision, the two vehicles lock together. Yep. And move off at 8 kilometers per hour. So we have the mass times the velocity afterwards of both. What is the mass of the unknown vehicle? What is the mass of the truck? So let's start putting in the numbers that we know. The mass of the car is 1,100, and it's moving at 20 kilometers per hour. So, interesting note. I'm allowed to use 20 kilometers per hour. I don't have to go into meters per second because it's a linear equation. If they're all kilometers per hour in the equation, who cares? As long as we use the same units everywhere in these equations, it will work. Afterwards, this is how I would solve it. Do we know the mass of both? Do we know the mass of both together? So I would just leave this as m. How many of you are tempted to go 1,100 plus m? Oh, that's good. I'm glad nobody's really jumping up and down over that idea. M. We don't know the mass of both after, but we do know they're moving at 8. Oh, man. That's even, the baby is dim-witted and fast asleep. You just swipe all that kid's candy. 1,100 times 20 divided by 8. $24.55? No.
27.
27?
27.50, sorry.
27.50? Okay. So M is 27.50. Now you just got a little bit of, Sherlock Holmes work to do here. Did anybody else get 27.50? Just to make sure. Now we have to figure out what the mass of the truck is. The car was 1,100, so a little bit of common sense says that this will be 1,100 plus the mass. This is both, right? Plus the mass of the truck. Not a very big truck. 1,650 kilograms. Yeah? Okay, so the mass of the truck. The answer to the question is 1,650. And that's it. There's two layers to this lesson. One is about all that, I was going to say nonsense. It's not nonsense. But all of that stuff, that cornucopia of elastic and inelastic and isolated and non-isolated. But this is the meat of the sandwich, this stuff here. All the other stuff is just kind of the topping. Applying the law of conservation of energy. So are the page numbers right here? Yeah. Okay. So on page 17 of your handout are a variety of questions. These almost all deal with applying the law of conservation of momentum. I see up here I'm using this symbol. How many of you have seen that before? Sigma. And it means total. Is there some kind of joke I'm not getting there? No? You're just excited to see sigma?
Yeah.
Some people will go their whole lives without ever seeing sigma. It's like the great white elk. Anyway.